Hey everybody, Mr. Ellinger here, and we're doing notes on accumulation and the FTOC. This is going to be a short version of what we would have done in class today, and we'll do a little bit of it on Friday for the A-Day class, just so you get enough of the gist of it, but then the rest of it you'll just be doing on your own. And this is mostly set in the context for how else are we going to look backwards from the derivative to the original function? Now, instead of looking at it algebraically, we're going to look at it graphically and see what the graph of velocity tells us about position, or what the graph of the derivative tells us about the original function. Okay? So here's an example. A truck travels along a highway at a constant velocity of 60 miles per hour. I drew the picture here to save myself some time. For 1.75 hours, how far did it go? And you might be like, okay, well, I could work this out without a graph, Mr. Ellinger. Well, the purpose of this is to illustrate that, to figure this out, you do 60 miles per hour times 1.75 hours, and the hours cancel out, and you get 105 miles, I think, if I did the math there correctly, really fast. But what does that represent graphically? Graphically, if you think about it, that's just the area that's under the velocity curve. So this is a graph of velocity, and on the graph of velocity, sorry, a text come in. On the graph of velocity, it's showing us how far the truck has traveled based on the area that's underneath this curve. The cool thing is that it doesn't have to be a straight line to do this. It also could be a variable velocity. So in this case, this instead is feet per second, and a truck is slowing down over an exit ramp. And so this is velocity in feet per second, and this stands for seconds. And the question is, apparently I got interrupted when I was finishing this. But the velocity is the y-axis, and the position is on the x-axis, and that's seconds. And the question is, how far did the truck travel? Well, that's going to be the area under this curve. It's still the area. It's just that the top of it, it's not a rectangle. The top of it is this thing. The cool thing is that we can just use our geometry and go, well, I can figure out the area of that without any fancy calculus stuff. I can just say, all right, this is 10 seconds at 30 feet per second. So it's 10 times 30. So that's going to give me 300. And it's 10 seconds and 30 feet per second. Again, the seconds would cancel out. So that gives you 300 feet. But wait, we were going over that for a while. And I can just use area of a triangle here. So it's 1/2 times the height, which is 30, times the length, which is 10. There we go. Oh, that's pretty easy. So that's 300, 150. So that's 150 feet. That's this area right here. And so altogether, I get 450 feet. Okay. So again, we're looking at the derivative, and we're asking, what can it tell me about position? And so just like we did last class with antiderivatives, we're trying to figure out how to go backwards from the derivative back to the original. What does it tell me? And what we've learned is that the area under velocity curve gives you the amount your position has changed. It gives you like how much has your location changed over this time. And in physics terms, that's called the displacement. How much has your position changed? I've moved 450 feet in that last example. And so area and accumulation, this is what we talked about before, talked about a little bit before, but just to say it, is that the area under a rate function, and for a moment, I'm going to say under in quotes, and you'll see why in the next example, is the amount of stuff you've accumulated. You'll see an example of why I'm saying it this way in just a second. So it's how much stuff I've accumulated. I've accumulated 450 feet in that example I just did, because the rate was measuring how much my how many feet I've moved for a given number of seconds, excuse me, times the number of seconds, and that gives me total accumulation of feet. Now, the reason why I put the quotes around the under is because under, I don't literally mean under, because like, you know, area under the curve goes forever. What we really mean is the area between the curve and the x-axis. So Estelle's using a jetpack and she's flying through the air and going up and down. And the function r of t, which is illustrated here, is the rate of change of Estelle's altitude. So it's her vertical velocity. She's going up and down. So this is velocity. And the question is, how much altitude did Estelle gain from 0 to 8? And you can work that out pretty fast. It's 40 times 8 over 2, so 160 feet. 40 times 8 divided by 2, just using area of a triangle stuff. So that's 160 feet. Cool. But then it says, what was the net change in altitude over these 16 seconds? So all the way to the end. And it's like, oh, wait, hold on a second. In this part, her velocity was negative. So she's not going up anymore. She reached a local maximum of height at 8, and now she's coming down a little bit. Whoa, okay, that's a little different. And so we could have a negative velocity. So we don't really mean under, although in casual conversation, people will say under the x-axis. Really, we mean between the curve and the x-axis. So if you're negative, we're going above, and this is going to stand for a loss of height because her velocity is negative. So the net change in altitude, well, she went up 160 feet in the beginning, but then she started moving down for a little bit, and it's 1/2 times the base, which is still the base, so that's 8, times the height here, which is only a negative 20. Excuse me, a little cough. And so for negative 20. So she went up 160 feet, but then she went down 80 feet. So altogether, that's 80 feet up, or net change in altitude. So, okay, this is a little different. So the curve could be below the x-axis, and that stands for a loss of something. In this case, it's a loss of height. And we could have other situations that we look at. Remember, we've been accumulating different things or having different kinds of rate functions. It hasn't always been a physics one. Excuse me. Sorry, still a little sick. It's not always a position one. Sometimes a position velocity acceleration. Sometimes we've got rate functions that are measuring different things. And that can be just as true with these problems. So this one, the rate is always positive. This is number of barrels per hour that's going through a pipeline. And I guess you could have some kind of pipe that was going in both directions. But in this case, the rate is always positive. So it's always flowing in one direction. And this is an example. I put this example in order just to show you something else besides position velocity acceleration. But still, the area of these boxes here stands for barrels per hour, the rate of oil passing through the pipeline, times hours. That stands for number of barrels, like accumulated barrels that we're getting. And again, this area is going to stand for how many barrels I've accumulated over this period of time. So the graphical big thing we're seeing is that the area stands for accumulation. The area, and when we say area, again, we have to remember, okay, there's positive area, and then we actually kind of have negative area. So, okay, that's a little weird. But the space between the curve and the x-axis stands for either a gain of stuff if it's above, or it stands for a loss of stuff if you have a negative rate. In this case, you could answer this one, batch, what the heck, I'm here. And so each one of these boxes is 6 times 1, so that's 600, 1200, 18, 2400. And then I could do a 1/2 base times height, and it just asks for approximate. Looks like the answer is 3,000 barrels. So again, what is the area under a rate function? It gives you accumulated stuff, whatever the rate is measuring, like how many feet you're gaining or how many barrels you're gaining or whatever it is that the rate function is telling you. So it's accumulated stuff. And again, it can be positive or negative depending on if you're above or below the x-axis. So under, people will say under, but they really mean between. And we say area. Technically in geometry, area is always positive, but in this context, in real life context, you can have a negative rate. And so you can have an accumulation that's negative because you're losing something. And then how can you find the units of the area? Just do the x units times the y units. And that tells you what the units are. All right, and then we're going to go into a second part. Might need a second video on this. We're going to go to a second part where we're going to find out how to approximate area with different kinds of rectangles. So what if we have something that we can't approximate normally? What we'll often do is we'll subdivide the area into smaller regions. And then we're just doing an approximation of how much area is under the curve, because this is not a curve that I know the geometric object for. And I know you might have another idea of how we could find the area, but for right now, we're just going to use rectangles. And so one thing we could do is we could do a left Riemann sum. And what we would do is divide up the x-axis into a bunch of regions. And then we'd use, the problem is we've got different y values. So how big a rectangle should we make it? And I know you might say, well, go halfway in between, or you might come up with some other idea. But on a left Riemann sum, you just use the left-hand y value to find the area of the regions. And in class, we'd have you work this out. I'll do this first one, but I'm not going to work out all the other ones just for speed. So what would the area of these rectangles be? Now I'm speeding it up, but this curve here is y equals x squared. Yeah. And so it would just be the width, which in this case is half a unit, because this is 1, 2, 3. And then the height, which for this first one would be 1 squared. The height's just 1. But then for the next rectangle, it would be 1/2 for the width times 1.5 for the height squared. I'm squaring it because that's my function, y equals x squared. And really, I'd plug that number into whatever my function is to find out what the y is. Then I'm doing this rectangle right here. So I'd use the left-hand one because that's what we're doing, a left sum. And so we'd use the left one, that's 2 squared. So 1/2 for the width times 2 squared. And then the last one would be 1/2 for the width times 2.5 squared. And obviously this is going to underestimate because we're missing all this area above that we're not counting, but it's just making an estimation. So this is called the left Riemann sum. It's dividing up the area into a bunch of regions, and just for simplicity's sake, using the left-hand y value, whatever that is, in order to specify what the height of that rectangle will be. Of course, you could have done a right Riemann sum, and in that case, you would use the right-hand y value for each region. In this case, that would be an overestimate because we'd end up overshooting, because although the right y value is correct on the right-hand side, it's overshooting for all this part in here. And so you're ending up with some extra area when you do that. And so we'd end up with an overestimate in that case. And the final one that I'm going to mention down below here, so we've got left-hand sum, we've got right-hand sum. The last one is you could also do a midpoint sum. And again, so this one, we're doing 4 regions, y equals squared x plus 1, that's this curve, from 0 to 4. So first I'll divide it up into 4 regions. And then I'm going to do a rectangle. And in a midpoint sum, you're just going to use the y value of the midpoint between the left and the right. So in this case, that first rectangle would look like this, and it'd be a width of 1 times the height, which would be square root of 0.5 plus 1, because 0.5 is my x value. And my next midpoint x value is 1.5, so the next one would be 1 for the width times square root of 1.5 plus 1. And then plus 1, and then square root of 2.5 plus 1, and I'm running a little low on time. And then you could also do 3.5 plus 1 for the last region. So left sum, right sum, midpoint sum. These are 3 different ways to approximate the area under the curve, which now we know stands for accumulated stuff. So we're going to learn more about how to find this actual area. Better stop here. I'm going to have to do a supplemental a little bit more, but it shouldn't be too long.